So we have for this section 5.2, the definite integral. We are going to define what an integral is. But let's just go back to the previous section. And what we have seen is that this limit of the sum of all the little rectangles that we can form under a curve, we can write it using sigma notation, or we can write it out as the infinite sum of all these little rectangles. This is rectangle number 1, this is rectangle number 2, and this is rectangle n if we're making n rectangles. And also the base is delta x, and the height of each of the rectangles will be f evaluated at some x that is in that little base. And we also have seen that we can compute the area of graph of velocity versus time, and when we find the area under the curve, what we're finding is actual distance, because distance is velocity times time. So when we do velocity times time, what we're finding is the area, and the area by definition is the distance when we're dealing with that curve. So it says, it turns out that the same type of limit occurs in a wide variety of situations when f is not necessarily a positive function. So let me show you an example where actually f, in this case the function v, is not a positive function. So for example, you are driving 60 miles per hour. You're driving in a car, you're driving, if this is your house, you're driving away from home at 60 miles per hour, and then remember that velocity is speed with a direction. After you reach your destination, you go back again to home, and that in that space will be your velocity will be negative 60 miles per hour. So you're traveling away for 4 hours away from home. So the question is, how far do you go from home? So you know that if you have a v versus t graph, the area under the curve will be distance, because this will be 60 miles per hour multiplied by 4 hours, and then you get 240 miles. So the area as a function, this area is 240. And the interpretation is that you are traveling away from home 240 miles. Now, what happens when we are looking at this function and we are looking at it and seeing that it's a negative function? Well, the area in here, because between 4 and 8 hours, 4 hours have passed by, this area will also be 240. But if we are talking about the sums of these areas, this area is positive, this area is also positive, but because it's below the x-axis, the sign of this area is going to be a negative one. And it doesn't mean that the area is negative, it just means that areas below the x-axis are going to be considered as negative. And the reason why is because look at what happens. Between 0 and 8 hours, where are you going to be, or how far from home are you going to be? Well, if you went in the positive direction, 240 miles, and then you went on the negative direction, meaning left, 240 miles, you're going to be back home. So the distance that you have traveled after 8 hours is actually 240 plus negative 240, and that will be 0. So after 8 hours, the question to how far are you from home will be 0. The answer will be, oh, I'm back at home, because I went away 240 miles and then I went back 240 miles, so I'm back where I was before. So it is not going to be only about areas. When the function is positive, it will be simply the area, but when the function is negative, it will be the area with a negative sign, just because it's below the x-axis. I know that you're dying to see what is the actual definition of integral, the same way you were dying to know what was the definition of derivative. So first we're going to define integral, and then we're going to see how that is related to what we have seen so far, how it relates to areas and how it relates to antiderivatives. But right now let's just define it, and let's explain the symbols. So in here it says the sum of all those rectangles that you can do with the number of rectangles getting greater and greater. That is going to be the definition of my integral. And the integral has a symbol that is an S that is very long, and that's called the integral sign. And it's gonna have several things, as I'm gonna show you in the next slide. So the integral has different parts. The function f that is inside the integral is called integrand. Now the numbers that are going to be located on the top and the bottom of this S sign are called the limits of integration. And the one in the bottom is going to be the lower limit, and the one on top is going to be the upper limit. Now dx right now it doesn't mean anything. The same way where it didn't mean anything for us yet when we were taking the derivatives. Derivative, remember, is y prime or dy over dx. So it is just part of the notation. Later on it's going to be useful, but this is just to show you that the integrand is going to depend on x, and if you have any other letters in it, those may be considered constants. So if you have an expression here, if it depends on x, then it will say dx. If it depends on t, then it will say dt, and so on. So now we're going to see, as I mentioned just now, the integral of a function that depends on x may be written as a function that depends on t, and that's when we will have written dt. And if the function depends on r, then there will be a dr at the end. It is very important that you write it when you are writing integrals, so this is something that you cannot forget. The same way you cannot forget, for example, I don't know, it is just important about the notation. Oh, yeah, the same way that if you're writing f of x, you cannot forget the parentheses. You can't write f x. You have to write f parentheses x. So it is just symbols, and you need to keep them. Now, whenever we have the sum of all these rectangles that can be made for any function to approximate it, this sum is called a Riemann sum, and it's because this mathematician Riemann invented those. So we're going to call that Riemann sum, the same way we call Pythagorean theorem. So that's a Riemann sum, and we can have a Riemann sum using right endpoints and left endpoints. So it says now the definite integral of an integrable function. We're going to talk about what this is. It says can be approximated to within any desired degree of accuracy by a Riemann sum. Remember that we were able to take only 4 rectangles, or only 8 rectangles, or 10 rectangles, and if we use a computer we can use 1,000 rectangles, or ultimately we would be able to write an expression for this so that we can actually find the limit, because we know how to find the limit now. It says we know that if f happens to be positive, then the Riemann sum can be interpreted as the sum of the areas of the rectangles. So if f is above the x-axis, then the Riemann sum is going to be a positive number, and it's going to be the sum of all these little rectangles right here. Since we want the maximum number of rectangles as possible, then what we have is, the more rectangles that we have, the areas are going to approach ultimately to the area of this shaded region. So therefore this integral can be interpreted as the area under this curve. So what is the area under this curve? The area under this curve is actually the integral between a and b of the function f of x, which right now for this example I don't know what f of x is, and to indicate that this depends on x, I write the x. So if this area measures 64, I don't know, whatever it is that you want to measure in whatever units, then that means the integral between a and b of this function is 64. So as I mentioned before, if f happens to have positive values and negative values, and then maybe again more positive values, the Riemann sum is going to be the sum of the areas that lay above the x-axis minus the areas of all the rectangles that lay down below the x-axis. So the integral, if I'm integrating all the way from a to b, this as a number will be the area that I have here plus the area that I have here, which I'm going to call A1, and I'm going to take away the area that appears below the x-axis, which can be called A2 right here. So for example, a small exercise, let's say that the integral of this function is 1, and you know that the areas of these two little pieces is 4. How much the area in this section would be worth? Well, I know the integral is worth 1, and the integral includes these two pieces of area minus this area. Then this whole area will have to be 3, because 4 minus 3 is 1. So if this is worth 4 and this is worth 3, the integral is worth 4 minus 3, which is 1. So in general, remember that we could pick any x's. If I have a function and I have a rectangle, I can pick any x within the base of the rectangle, so that I can pick that one, and that will be my height, the height of my rectangle. The other thing that we could do is not only to use intervals that have the same base, we can also choose intervals that have different length to accommodate the rectangles in a better way. So if we're using different length, or different width for the rectangles, we may have as many different intervals as we want. Then the limit has to be changed a little bit into I don't want not only n to approach infinity, I also want the interval, the maximum interval that you have to approach 0, because then I'm making sure that the width of this rectangle is as small as it can be. So if I make sure that the maximum of it is approaching 0, then all of the other ones, even though they are unequal parts, are approaching 0 as well.